Good evening, everyone. I welcome you all to NPTEL live session for Aspen Plus software. So let's wait for 5 minutes. After that, we will start. Basically, we are waiting for some students to join. Okay, so let's begin. We have waited enough. So, good evening, everyone. I welcome you all to NPTEL live session number 5 for the week 5. So, we are like having classes for Aspen Plus simulation software, a basic course for beginners. And the course instructor for this course is Professor Prabir Kumar Shah. He's from IIT Guwahati, and I'm this course TA Amit Kumar Sharma. So as you all know that every week on Sunday from 7 to 9 we have a live class. So in this session we cover previous week's like basic course content and we solve some sample assignment questions. So these questions are very helpful to you to understand like what type of question be in the assignment or exam and how to solve them. This meeting is being recorded, So this PPT and the recording of this meeting will be shared to you from the NPTEL team. Okay, so those who are not able to join today, maybe they can have a look into the video. So this recording will be shared. Okay, let's start. So as of now, from previous class, we have covered like the usefulness of Aspen Plus in modeling physical properties, then about model pure binary and ternary and multiple mixer system. So we have covered up to here. And today, so we will look into this plot relevant data. Okay, this PT envelope, ternary diagrams, PXY, XY, and all, and the manipulation of raw theoretical experiment data via regression. Then about NIST thermodata engines and DCAMA, and the reporting relevant results and all. So we will look into these things. Okay, let's start. So we have in Aspen, we have some analysis tool. So like we have some components. So each component have some their basic properties. So we can run some property methods and we can analyze the properties of those particular component or mixture and all. Okay, so it's basically used for generating simple property diagrams for physical property models and their data. So using this analysis tool in Aspen, we can generate simple property diagrams, okay, for physical property models and their data. So the following diagrams can be drawn. So this tool can be used to draw for like pure component. So pure component means there is one component like paper, pressure versus temperature. So like we can generate a diagram for pure component properties like vapor pressure versus temperature. We can draw a diagram for PT envelope. Okay, we can draw diagrams of binary mixtures. In the binary mixture, there will be two components. So we can generate TXY and PXY. And the mixtures, so if mixture, so then like if like two or three components are in a mixture, so we can generate diagrams for the mixtures also. In the ternary diagrams systems, there will be three components. So in binary two, pure component one component, and ternary there will be three components. We can generate residual curves, phase diagrams, and all. We can also draw the solubility diagrams. So these are the application of this analysis tool. The inputs and the results are saved as a form in the analysis folder for later use. So the results of this analysis are saved in a separate folder, which you can use later. So like pure component analysis, these examples were solved in the class. So the first is around the density of acetone at atmospheric pressure and temperature is given, then use NRTL property method and valid phase are liquid and vapor. So we will look into these examples. These examples were solved in the class, so you can refer to the video. And if we have time after solving the assignment questions, we will come to these questions. Then the PT envelope. So in the PT envelope, like pressure versus temperature diagram. So P for pressure, T for temperature. So it's a pressure versus temperature diagram. So it is at the fixed composition. So like we have some fixed composition. Like if we have a mixture, then will have a ratio like 1:1. Like if you have methane and butane, then the methane to butane in ratio like 1:2 or 1:3. So we have a fixed composition. We can use that composition to draw the PT envelope. It's applicable only for the vapor liquid system, not for liquid liquid system. It's important. So it's applicable for only vapor liquid system. Okay, not for liquid liquid system. So if your mixture in the given range will be in like suppose liquid liquid only, then it will be not valid. It is only valid for the vapor liquid systems. It forms of envelope for mixture components that differentiate that area of liquid vapor and a vapor liquid mixture. So basically this envelope, like suppose if there is an envelope like this, so maybe this area will be the liquid and this will be the suppose vapor and this will be liquid and vapor mix. So it will form like envelope. Okay, so in this envelope the both phase will be in coexistence. Okay, so it forms of envelope for mixture component that differentiate the area of liquid vapor and a vapor liquid mixture. So you can see this area This area and this area, both all these three area are having different phases. It can mark for 0 to 100% vapor. So it can also, like vapor fraction, it can give us the detail like at which point the vapor fraction 0 to 100%. We can find all the details. So we have two examples also. So these examples were solved in the class. You can refer to the class notes. If you have enough time, we will visit to these examples. Then the binary analysis. So in binary analysis, it is for two substance only. So basically, as names just binary, so there will be two substance. So it's only for two, not for three or one. So in this, we can have like TXY, PXY, or Gibbs energy of mixing. And the valid phases for this binary analysis are vapor liquid, vapor liquid liquid, vapor liquid with free water, vapor liquid with dirty water. So these kinds of phases we can consider in the binary analysis. So like vapor liquid, vapor liquid liquid. So as you, if you compare to the PT envelope, then in that liquid liquid is not possible. Okay, only vapor liquid was possible. But in binary, we can have vapor liquid, vapor liquid liquid, vapor liquid with free water, and vapor liquid with dirty water. Okay. Then the TXY diagram. So temperature varies. So in this TXY diagram, temperature varies, but pressure is fixed typically at atmospheric condition. So in this, the temperature will vary, okay, and pressure will be fixed. So normally at atmospheric condition. XY composition of species I will be shown. So like if we have XY mole fractions, okay, so one of the species will be shown. So species I will be shown. Lower line present X in liquid phase and upper line presents Y in the vapor phase. Important. So lower line present X in the liquid phase and upper line presents Y in the vapor phase. Inside portion of the envelope will present vapor liquid mixture. Upper line represents dew line and lower line represents the bubble line. So these are some info about the TXY diagram. In PXY, the pressure varies, but temperature is fixed, typically at atmospheric conditions. So in PXY, the pressure varies, like P, it is varies, but the temperature is fixed, typically at atmospheric condition, like 25 degrees centigrade. XY composition of species I will be shown. So the I will be shown. Upper line presents X in the liquid phase and the lower line present Y in the vapor phase, and inside portion of the envelope will represent water vapor, sorry, vapor liquid mixture. The lower line represents dew line and upper line represents bubble line. Then in the Gibbs free energy diagram, a process or reaction occurs spontaneously if the Gibbs free energy is decreased. So we know that the Gibbs free energy is if the energy is negative, it means the reaction is spontaneous. And like suppose if we are having like two, three reactions and one reaction is having more negative Gibbs free energy, then it means that that reaction is will happen first. So the more the Gibbs free energy is negative, more the spontaneity of the reaction. So a process or reaction occurs spontaneously if the Gibbs free energy is decreased. So if you are having a mixture and the mixture is like if the energy is decreasing, then this process will be spontaneous. The change in the Gibbs free energy of mixing is always negative. Okay. Otherwise, the mixing would not occur at all. It is a fact that Gi less than GiO, where G is the Gibbs free energy, I is the index of a component in a mixture, and naught represents the pure component. So it's for the Gi less than should be Gi naught. Okay. So it's represent the pure component and this represent the mixture. So the mixture Gibbs free energy should be negative. Let me check. Some students are there. Okay, so we have students. Is my slides are visible and my sound is okay? Anyone?
Yes, sir.
Okay. So let me know if you face any difficulty. Okay. So then the about Okay, just a moment. Yeah. So now in the mixture analysis, it is used for property evaluation for multiple mixtures from flash calculation or single phase mixture without flash calculation. So we can, in mixtures, we can do these things. Relevant tables and plots are generated and one or more property sets can be used. So this was the example. At the end of the class, if you have time, then we will go through the examples also. So in ternary diagrams, so in this diagram, we can have three components. Like in binary, we can consider two components. In ternary, we can consider three components. And the valid phases that can be considered in this ternary diagrams, that will be vapor liquid and vapor liquid liquid. So it's important. So for each analysis, you should know that which phases are valid for that particular analysis. Azeotrops, like constant boiling point mixture, is a mixture of two or more liquids whose proportion cannot be altered or changed by simple distillation. So for the azeotrops, we can draw the ternary diagrams, the binary azeotrops and ternary azeotrops. So these are the examples. For the examples, you can refer to the class notes. Residue curves. So this analysis is used to generate residue curve maps. These maps plot the composition trajectory of ternary mixture undergoing distillation and total reflux. Okay. And these maps are also used to visualize the presence of azeotrope in a mixture. So with these residue curves, we can visualize the presence of any azeotrope in the mixture. And one can also use residue maps for predicting visible splits, selecting internets, and analyzing the potential column operability problems. And residue curves should be used with non-ideal chemical system and property methods that represent such systems. So these are about the residue curve. So there is also an example. Then a data and regression tool. So in Aspen Plus, we can use some experiment data. Okay, so Aspen Plus have some databases as we have discussed earlier also. DKMA and this like I think NIST. Okay. Okay, I think the name is NIST or let me check. Okay. So you can use the database to find the experimental data. You can use the data and you can also use the data like and you can use the regression to like to find or like to extrapolate the data. So you can use the regression, you can use already available data. Okay, you can use the experimental data to regress and do the regression, and you can extrapolate the data. So we have like United States National Institute of Standards and Technology, NIST, and thermodata engines and DKMA. So these three are there. Okay. And Aspen Plus has a long-term collaboration agreement with the NIST. So yeah, NIST database. So with the NIST, Aspen is having long-term agreement. So you can directly use the NIST data. Okay, you don't have to pay anything for this. But if you want to use DKMA, then I think you have to pay something. So in the NIST data bank, you will go to the data bank. You can find you can select the component there. Then it will show you the data. We will look into these also. So it is a huge database for thermodynamic properties, transport property, and phase behavior. And also the thermodynamic data correlation, evaluation, prediction tools. It includes over 24,000 pure components and 30,000 binary mixtures and is absolutely free for Aspen Plus. So for Aspen users, this data bank NIST is free and it's having huge database. Okay. And azeotropic pressure, binary diffusion coefficients, binary liquid-liquid equilibrium composition, binary vapor-liquid equilibrium composition, isobaric and isothermal, you can use these data. And you can find critical pressure, temperature, like density, enthalpy, specific heat at constant pressure, surface tension, thermal conductivity, and viscosity. So you can have all these data using this data bank. And this NIST data are broken into 4 blocks. So it's basically in 4 blocks: phase diagram, volumetric, energetic, and other. So in phase diagram, like triple point, critical temperature, phase boundary pressure, okay, and volumetric, critical density, saturated and single phase density, and the volumetric coefficient. In energetic, energy differences, energy derivatives, speed of sound. In other, transport properties, surface tension, refraction. DKMA is abbreviation of, it's a German, I think. Yeah, it's for German Society for Chemical Apparatus. Required subscription for or pay per dataset online purchase. So if you have subscription, then you can use the subscription So you can register in this DKMA website. You can purchase subscription. So based on that subscription, you can use data regularly. And suppose if you want only to purchase single data set, then you can directly purchase. You can pay per data set also. So we have also the tape poly. So table data using a polynomial. If you have a polynomial, you can use this data. Okay. So the table data direct use and interpolation of user supply table data. So you can directly use this data, or you can also do the interpolation, the polynomial coefficient calculation from a general polynomial model. So if you have this data, so you can also generate a polynomial. Based on that polynomial, you can find more data. Okay. Then the regression. So in the regression, determine the parameters of physical property model for from experimental property data. So if you have experimental property data, you can use this regression method of finding the best fit among various mathematical models. You can compare the results and you can find the best fit among various mathematical models. It can be used for measured data for pure component as well as multi-component system. Almost any kind of experiment data can be fit, such as vapor, liquid equilibrium, density, specific heat, activity coefficient, and all. And experimental data can be self-generated or from NIST or DKMA. So if you want to do the regression, you can either use this data sets, or if you have your own experiment, you can use that data and do the regression. Calculation type can be either evaluation or verification or regression. So you can, these types of calculation are available in this regression. Okay. Then we can also do the property estimation. So if the required parameter is not in there in Aspen physical property system data bank, so suppose if you are having some particular component and that component is not specified, those properties are not specified in the Aspen data bank, then you can enter it directly. Okay. So you can enter directly from books, journals, or any other literature. You have that properties in the literature or journals, you can use that data and you can feed into the Aspen. Found through data regression using experiment data, you can done the regression and you can found the properties from there. You can estimate using a nice database. You can estimate using property estimation. So there are multiple methods by which you can find data for a particular component that is not defined in the Aspen database. It is done for new components or unusual components. It uses a combination of experiment data and molecular structure. So if you have molecular structure, we can find the data. We can enter that particular molecular structure, all the details from the internet, from the literature, okay, from the books or journal, and we can define that in the Aspen, and we can use that data for our calculation. So a few typical estimate properties through property estimation method are like pure component physical property. You can define this pure component thermodynamic properties, pure transport property parameters, temperature dependent model parameters, binary interaction parameters, and unific parameters. And other are normal boiling point, critical pressure, temperature, volume, heat capacity of ideal gas, liquid and solid. Then the Gibbs free energy of formation, vapor pressure, enthalpy, and all. Now the molecular editor for conventional components. So we have also a molecular editor for the conventional component. So specify the connectivity of each atom in the compound or import .mol file from the internet. So if you want to define a particular component itself and want to edit, then we can either, like, there is a website chemical book. So from that chemical book website, you can find the component, you can download the structure file and you can import into the Aspen, and you can use that particular, or you can edit the conventional component. So these were the examples discussed in the class. So we will look into it after the assignment discussion. So okay, let's start with the question. So I request you all, please open your Aspen Plus, because question will include the Aspen. So open the Aspen, then let's start with the question. And after solving all the assignment question, we will go into the examples that were in the previous slides. Question number 1 is, in PT NRO diagram, P in the y-axis vapor phase just above the boiling point curve. True or false? Your sound is not clear, Rajesh.
Sir, true, sir.
False.
So we have two answers. One is true, one is false. So I would like to hear the reasoning behind your answer. So first, the one that is saying true, please explain your reasoning. Why? Okay, so the one who is saying the false, please explain your reasoning.
Sir, in PTL Valley diagram, the vapor phase rests right side of the boiling point curve. The
Pardon,
right
please
side of the
repeat.
boiling point curve. Sir, in PTL Valley diagram, the vapor phase rests to the right side of the boiling point curve.
Okay, to the right side. Okay. So suppose if this is the PT envelope, so you mean to say like this will be the paper, right? Right side.
Yeah, you're right. Right, right.
Okay. And this will be the liquid region, and this will be the liquid plus vapor region. Okay. So the vapor fraction for this one will be 0 or 1. This line. What should be the vapor fraction for this line? 1.
One.
And for this, the vapor fraction will be 0. Okay. So the PT envelope diagram, vapor phase rest above the boiling point curve. Okay. True or false? So it is not above, it is, you can say below or on the right side. It's false. This is the figure. Figure 3 is a snapshot of the diagram produced after a property analysis. Answer the following 4 questions. Is the figure clear to you, everyone?
No, sir.
Sorry, it's not clear? Okay, so are you able to read this data? What is written here? Are you able to read the component's name and all? If you are not able to read, I will zoom it. Please let me know if you are able to read these names.
Okay.
Okay. I think everybody is able to read. So the question is, pure component analysis had been performed in vapor phase. True or false?
False. It's liquid, sir.
Okay, let's wait for another like any other answer. Anybody is having other
Yeah, it's
opinion?
false. Should be in the liquid
Yes.
phase we can measure.
Okay. Please explain your reasoning.
Sir, in the legends, you can clearly see it's liquid CV water and liquid DGFL ethanol.
Okay. So in the legend itself, you can see liquid. Anybody else? Okay, so we can see it in the legend itself. So it's false. So this the same figure. We have another question. The question is, which among the following is the property type that have been analyzed in the run? So the property type, okay, which is used to analyze in the previous picture, and the options are colligative, EOS alpha function test, thermodynamic, and transport. So these are the options.
Thermodynamic.
Okay, let me go back to the picture. So if you want to see the picture again, here is the picture. Just see it carefully, and then I will go back to the question. You can, I think you can read the legends, you can read these access. So let's go back to the question. So which among the following is the property type that have been analyzed in the run? Yeah, so what is the answer? One of you was saying thermodynamic, right?
It's measuring specific heat and
So it's mentioned here, it's specific heat at, yeah, CV, specific heat at constant volume, and the other one is is it DG? Okay, so these are the thermodynamic properties. I think one of you is saying something, but your sound is not clear. Please check your mic.
Yes, sir.
Yeah, now we can hear you. Please repeat. Okay. So the correct answer is thermodynamic properties. The properties analyzed in the run are the constant volume heat capacity for a pure component, enthalpy departure flow for a pure component, free energy departure flow for a pure component, and mass constant volume heat capacity for a pure component. So let me know the answer.
Sir.
Sorry? Your sound is not coming. Rajesh, I think you were saying something. Your sound is not okay. Please check your mic. So it is A and
B, sir.
B, A and
C.
B. C. Okay. So let me go back to the, yeah. So this is the graph. So if anybody don't know about this DG, so you can try the Aspen help, try these names, maybe you will get some help. You can do that, okay? Try to use the Aspen help. Let me know the answer. So one, I think it is mentioned here, CV, so it's very common, constant volume specific heat. And the other one is the DG. You can use Aspen help to know about the name DGFL. So we have answer one is we have constant volume heat capacity of pure component. Okay, the other is we have one option. I think free energy
departure flow.
Yeah, so free energy departure flow for a pure component. The correct answers are A and C. Which among the following are being analyzed in the run? Acetone, ethanol, methanol, water. So you have 4 options. Let me know which of these components are being analyzed in the given run.
Ethanol and water.
Okay, it's
Ethanol and
direct.
water,
So
sir.
yeah, it's you can see in the legends. Okay, so it's ethanol and water. Now we need to use Aspen plus. Okay, so take 5 minutes. Obtain a PT envelope for methane, butane. So first open Aspen, use new simulation, define the components methane and butane. You have given a mixture 1:2. You have given a method, Peng-Robinson property method. Use this method. Answer the following 2 questions with accuracy up to 3 digits after decimal point. The first question is bubble point of the mixture at 75 bar is. So you have given the component's name, you have given a mixture, you have given a ratio, you have given a property method. Now you need to analyze it. Okay. So you don't need to go to the simulation environment, just be in the property environment only. Define the components, define the method, then use the analysis tools. Okay, and do the analysis and let me know the bubble point of the mixture of this particular mixture in this particular ratio at 75 bar. So take 5 to 6 minutes, try it in Aspen and let me know the answer. Everybody, please try. So we have around 9 students now. So I request you all, please try and I should have 9 answer at least.
Five degrees Celsius.
Okay, so we have one answer. So let me write it. Answer number 1 is 5 degree.
55 approx. 55.
55. Okay, so we have one answer 55.
55.622.
Yeah, because in the question it's mentioned after 3 digits after decimal point. So it's better to say your answer like this 55.662. It's better to answer
622.
because
622.
622. Okay, because maybe this can be wrong because maybe the limit is for 55.5 to 55.722 like that or 750 like that. So because it's clearly mentioned in the question, accuracy should be up to 3 digit. Okay, so it's important. So we have 2 answers now.
Yes, sir. 55.622.
Yeah. So we have 2 answer 55.622. 7 more to go. Just you please just use a new simulation window. Define the components. You have given components methane and butane. Just define the components. Use the Peng-Robinson method. Okay. Then just go to the analysis window. Then there is an option PT envelope. Click on that option. There will be a window. It will ask you some inputs. So you have given 1:2. Okay. Use these inputs and draw the PT envelope. And from that envelope, You can zoom it.
55.024.
Yeah. Third answer we have 55.024.
024.
So we have three answers. Four more to go. Anybody is like facing any issue in that? Please let me know. I need at least one more answer, then I will start the solution. Okay, last 1 minute. Okay, so let me start. Is my screen visible? Okay, so just go to the new simulation. Okay. Now in the question, if you see carefully, you mentioned methane, butane. Okay. Components you have mentioned it. Just define the components. Methane, inter, butane, inter. So now you have defined the components methane and butane. You can see the type, name, okay, CS number. It seems everything is okay. Go to the next. Then in the question you have given, you have to use the Peng-Robinson property method. So just select, so find the property method. It should be the Peng-Robinson. Yeah. So Peng-Robinson. Click on it. Okay. Click on next. So you can see the component. Okay, methane, butane, IJ, and all. This is the source database and run it. So you have defined the interaction and all. Now here you can see the analysis window. Okay. So this is the analysis. Here you can see the pure, binary, mixture, solubility, and PT envelope. So this is at home option. Okay. So if you go to the home, then there is an analysis window. You can find PT envelope. So go to the PT envelope. Then you can see here, you can see it's half red, half white. So it means the inputs are incomplete. You need to do the you need to enter the inputs. Then you have given the component's name, the flow rate. So you have not given a particular flow rate. So you have to maintain this ratio, 1:2. Okay. So just maintain this ratio. So methane, let's say 1, butane, let's say 2. Okay. Valid phase, PT is for vapor liquid. It's okay. Then let's start initial pressure. Make it 1 bar. Okay. Then just do it. Run analysis. So now you can see this is the PT envelope. So on the bottom axis, x-axis, you can see the temperature variation. On the vertical axis, you can see the pressure. So if you go to the question, then you have mentioned the bubble point of the mixture at 75 bar. The pressure under consideration is 75 bar. So you need to focus on the 75 bar. And if you focus here, so this green one is the vapor fraction 0. It means after this it will be liquid. vapor fraction 1. So this blue one is vapor fraction 1. So below this it will be fully vapor. In between this envelope it will be vapor and liquid. Okay. So now the point under consideration is 75 bar. So look at the y-axis. You find it 75 here. So if you see like this 75, so it's coming around this point. So around 55. But we have mentioned in the question, your answer should be accurate up to 3 digits. So what you have to do, just zoom it. Okay, or you can also do one thing, you can just click on it. If you take your point to this point, so just I think it will show you the XY coordinates. Okay, let's zoom in. So 75 bar, so it's here 75. So yeah, you can see the points. It's y is 74.851, but we need 75. Okay, so just zoom it more. So now you can see the 75 is here. Okay. So
We
you
can
can,
use tracker.
sorry?
We can use tracker. Right click
Tracker.
and show tracker.
Yeah, show tracker. Yeah. So yeah, it's good. So you can use tracker also. Yeah. So you can see 75 here. Okay, it's 55 point. Yeah, 55.50192. Okay. So you can do like this, or let's see other options. So we have tracker, y-axis map, and also we have some options here. You can explore these options. Okay. And you can also go to the, I think, the analysis. Okay, so there is also a result tab. So in this also, if you go to the like, it's, I think it's a different thing. Yeah. Okay. So from here we can see the point, okay, from the tracker. The answer will be around 55.622. Okay. So its range is 52.5 to 57.5. So any answer between this range is correct. Is it clear to everyone? If anybody is having any issue, let me know. Okay, I think it's clear. So next question is dew point of the mixture at 5 bar. For the same question, what is the dew point of the mixture at 5 bar? Okay, the answer is already visible, but you need to find it. The dew point of the mixture at 5 bar.
34.11.
How much?
34.11 degree.
So
One
for the,
0.01.
okay. So the point is that for dew point, first of all, at which point you need to see? On the green line or on the blue line?
Blue line, sir. Blue line.
Why blue line?
Bubble point line.
So this is a dew point line. This is a bubble point line, green one. Okay. So on the blue line, the temperature we have given, the pressure we have given 5 bar. So right click, show tracker, zoom little bit. Look at, okay, the 5, so it around here. So 34.12. Okay. So yeah, your answer would be in this range. So it's correct. Somebody's unmuted. Please mute yourself. Some background sound is coming. The next question is, change the ratio of methane butane mixture to 2:1. So change the ratio of methane butane mixture to 2:1 and obtain the PT envelope again. Okay, and answer the following 3 questions. So the same question, same components, but now the ratio is different. Okay, it's 2:1 now. Earlier it was 1:2. Now it's 2:1. So do it again with 2:1.
minus 44.91.
So we have an answer minus 44 point. How much? 919.
91.
We have an answer minus 44.9.
44.93.
Okay.
No, sir.
So
1 sec. They have asked for bubble point, na? So it's 83.
okay, so we have bubble point. So we have third answer is 83. So we have like totally different answers. So the guy who is saying 44, maybe you want to review. For the guy 83, either you can review. Just take a 1 minute and let me know the final answer. The question is bubble point of the mixture. The bubble point.
So sorry, sir. Sorry, sir. It's 84, 44, 44.
It is near
Okay.
to 40 minus 44.
Okay, so let's see. The answer is minus 47.5 to 42.5. So your answer is in between the 10. It's correct. So let's see. If you want to see the bubble point, just first go to the inputs. So on left side, you can see the inputs. Just change it. Now we have methane 2, butane 1. Okay. Then run analysis again. So now we have different curves. Okay. Different envelope. So we have given it's 75 bar. Okay, the bubble point. So which line is the bubble point line? Green or blue?
Green.
So just show tracker, then around 75. It's here. Okay, minus 44.82. Now the dew point of the mixture at 5 bar. So what is the dew point for the same question? Dew point of the mixture at 5 bar. What is the answer?
9
3.
point 10.
10.25.
10.25. So it's 7.5, 12.5. Okay, so the similar you can just dew point. So see the on the dew point line mixture at 5 bar. So zoom it. Okay, and you can see at the 5 bar. Okay, So now look at the result tab. The dew point of the mixture at atmospheric pressure is. Now if you go to the result tab, then let me know the dew point of the mixture at atmospheric pressure.
Minus 26.7. Minus 26.76.
Minus 27, sir.
Okay.
Answer.
So if you go to the analysis tab, okay, then this PT envelope, then here we can see some like system tab, tabulate, properties, diagnostic, and result tab. So here is the result tab is there. So if you see it, we have given mixture at atmospheric pressure. Okay, so let's change it to the atmospheric. Okay, you change it, then you can see minus 27.032. Like it's near atmospheric will be around here. 1 bar. Okay, so it will be near this range. Okay, so the range is minus 26.77 to minus 26.75. Yeah. What was your answer? 26.76. It's correct. Okay. Anybody else? Okay. So in the properties environment, which among these are options in analysis object manager? So in the properties environment, which among these are options available in the analysis object manager? Open your Aspen and go to this analysis object manager and see the options available.
Regression.
Sorry?
Regression.
Regression. Okay, so we have one answer, regression. Anybody else?
PT envelope.
PT envelope, okay.
PT envelope.
Okay. So if we go to the Aspen, then we can see here like we have a navigate manager and tools manager. In tools, we can see method assistant, okay, clean parameters and all. In the data source, we can see NIST, DKMA, DAP, PPR. And in run mode, we have analysis, estimation, and regression. So here we can see the summary and input history report. In analysis, we have pure binary mixture, solubility, PT envelope, and turn diagram residue curves. Okay, in the plot, we have custom plot and all. So here we can see the PT envelope. What about this generic? So history is not there, regression is not there. So one is there for PT envelope. What about the generic? Anybody? What is the meaning of generic? Okay, I'm also not aware of this actually. So the answer is generic and PT envelope. So generic is also there, but I'm also not aware. If any of you know, please let me
Maybe
know.
this is old version of Aspen. It has that
Yeah,
option.
yeah, that's why. Yeah, because in my Aspen also in the old, maybe the older version it was option. So that's why I'm not aware. If your option is your Aspen is having this option, let me know. Okay, so maybe like if you are for your exam, so in that exam the question will be from your Aspen only. So don't worry, you will not have these kind of question. So these are like previous assignment questions. So maybe it is from Aspen 10 or 9, I don't know. So that's why we are just considering maybe in any of version, this option is also there, but not now. So if you check now, so the in Aspen 12, the options are these. Okay. While analyzing the PT envelope, which among these may be specified? Start point, end point, valid phases, method. So we just did a question on PT envelope. So just let me know the
Valid
answer.
phases.
Okay. So we have one option, one
And
answer,
method also.
valid
Method
Valid
also,
also
property
this.
method.
method
everyone,
also. Okay.
sir, all four.
All four. Okay, but I don't think so. We have defined endpoint. Have you defined that?
All except start and end point. Valid
Okay.
phases and method.
Okay. Just maybe like because we have
Valid
multiple answers, so
method.
it's better to go back to just again to the PT envelope and check and let me know because we have multiple answers now. So just quickly go back to the PT envelope analysis tab and let me know. Let's check what kind of options are available there.
Valid phase and method.
Okay, so let's see.
Uh,
So valid phases and method. So these two options are there. Okay.
but sir, listen, sir, we can also do a input of start point as initial temperature and final temperature, so that can be done instead of
So if we
uh,
open it,
It's
specifying
initial
maximum point.
temperature and initial pressure.
okay, so initial pressure is there. Okay, but so the start point and end point. So the start point, the meaning of start point, maybe some of this may be specified. Okay.
It means the start point and end point of the curve, right?
Yeah. So
They
it's
don't
not.
need for that. They don't need for that.
So basically, we just need these valid phases, and we can start point, end point. It is not directly, I think, linked to this like this initial pressure and all. I think, yeah. Because start point of what? They have not specified it clearly. Okay. So
Sir, it is there in pure analysis, not in this one. In pure analysis, you can find start and end points.
but it's given PT envelope, na? While another PT envelope. So we don't
Yeah,
need
that's
to.
what. This is correct. Yeah, that's what.
Yeah, answers are correct.
Yeah. So we want to go into the PT envelope only. So in PT envelope, there is no option of start point. So if there is specified, it's initial pressure is mentioned, but not start point like that. If you go to the pure, I think I think option is there. Okay. So yeah, here in pure, there is start point and end point option is there. So don't confuse in this, okay? It's the PT envelope option is the method, the valid phases, okay? The initial pressure you can give, but you can not say the start point, okay? So binary analysis can be done with more than two components, true, false.
True.
Oh, nice. True.
False.
False.
So we have two options, two answers, true and false. So just I will give you 1 more minutes to rethink who is saying true and who is saying false. Let me know which one is the correct.
I think it's true.
Okay, so let's start. So why do you think it's true?
Yes, we can add multiple components, but interactions will be two components only. You can do it separately. The method shows interactions between two components, each two components.
Okay, but do you in the binary analysis at a time there will be only two components, no? Like suppose if you have a
Yes, yes.
okay, so you are thinking in that direction. Anybody who is saying false? What is your reasoning?
At a time, sir, we can analyze only two components in binary analysis.
Yeah. So as name itself mentioned binary and ternary. So in binary we can only have we can done the analysis, okay, only for two components. Okay, that's why it's the binary. The ternary we can have the interaction and all with three components. We can do the analysis for three components. That will be under ternary. So it is false. So we cannot analyze more than two components. And it was covered in our slides also in previous slides. Okay. So if you also go to the, I think binary. So here also you can see the components, only two components are possible at a time. So we are talking about the analysis. So in the analysis, this is the binary analysis, you can select only two components, not three. So methane, butane. So either component one can methane, two will be butane. Okay, so you can have two components only, not three. While performing the binary analysis, which among these may be chosen as analysis type? PXX, PXXY, TYY, TXXY.
Two and four.
So we have one answer, option B and option D. Option B and
Yes,
option D,
B
we
and
have
D.
two answers.
B and D.
Okay.
B and D.
Please check everyone. You have Aspen, just
All of
go
the
to the binary analysis. All of the above.
yes.
Okay. So
D.
we have one more answer, A, B, C, and D. Okay. So now we
D.
have two. Sorry.
B and D.
Okay. So we have three
Answer
B and D,
B and D.
and like one of you is saying all four. So those who is saying like the one who is saying all four, please check your answer because we have more vote towards B and D.
Yes, sir. B and D is correct.
Okay. So now everyone agree towards B and D, or anybody else having any other opinion?
Agree, sir.
Okay. So everybody is agree. So yes. So the correct answers are B and D. If you go to the binary analysis, so we are at binary. Okay, so here you can see the analysis type. Okay, you can see it is TXY, PXY, TXX, TXXY, PXXY. So you can check here, gives energy of mixing. So just compare the options with these, you will know your answer. How many components need to be specified in ternary system? So we have already covered this. So for binary 2, for ternary 3. Okay. So we need 3 components, and the binary analysis generate in this manner in triangular shape. So the each vertices is representing a component. Suppose component A, this component B, and component C. Okay. So in that way, we can represent, suppose, a component having some amount of A, some amount of B, and some amount of C. Then that will be in this region. Okay. So suppose this is line number 1, line number 2, line number 3. Now let me know if a component have 50% of A and 50% of B. So what do you think where that component will be in this figure?
Online AB, sir.
Yeah, on line A and B.
And B.
Because yeah, so basically on line 1. So on this line around here, maybe in the middle. So it will be here because 50% of A and 50% of B. Okay. So basically, if like B and C, then that will be in this line, C and A this line. If it's having like here, then all the components are present like that. So you can do this ternary system. So just as we are talking about this ternary system, so you can use Aspen, and you can also use a software. There is a software fact says. I think many of you have heard this name. Those who are from chemical engineering, have you heard about it? Fact says. Anybody?
No, sir.
No.
Okay. So let me just show you then if you have not seen it. It's very interesting software, and it's also available on internet for education purpose. So you can do various analysis in this software, like similar to Aspen. Just a quick 2 minutes. I can show you something. System is very slow. Yeah. So these are the options available. So in the facts sets, you can calculate the equilibriums, okay, of like you can define components. So it is based on the Gibbs free energy minimization module, okay. So here you can use some components, some reactions, you can do the equilibrium. So it will show you all the possible results from that particular components, because like in Aspen we have to define the components. If we know all the components, because Aspen is limited to the your inputs. So suppose if I want to see the phase diagram of, so suppose if I want to see, like I have carbon, hydrogen, and oxygen. So I have 3 components. So I want to see a phase diagram of these 3 components, in which one vertices will represent the carbon, one will represent hydrogen, and one will represent oxygen. Okay. So from these CHO system, we can have many components. Okay. Because we have not defined, we have only defined the elements like carbon, hydrogen, and oxygen. So with different composition, we can have different elements. So in the Aspen, it's difficult to define all the components, but in fact says we can do this analysis. So if you define the components, then you can define the like temperature. Okay, like I'm looking at like 800 degrees centigrade atmospheric pressure, and if I calculate, then it will do the calculation and show me the all phases. So now you can see. So this line is basically, so you can see the above, there will be some carbon deposition because there will be solid carbon will be there, and below this line there will be only gases. Okay, so you can do more things about this. So in this, if you want to, you can also do the equilibrium calculation and all. So you can explore this. Those who are interested, just go to the website and you can download and you can play with it. So it's a very good software, yeah. Okay, so you can also use this and you can verify the result of Aspen with fact cell, so it will be similar. Okay, so for ternary diagram, you can use Aspen also, you can also use the fact cell. But the education version is limited only for 3 components. So if you are interested in like more components, then you need to get a subscription for that. So what options are available in the selecting valid phases for the generation of ternary diagrams? So if you are using ternary diagrams, then what are the valid phases? Vapor only, vapor, liquid,
C and
liquid,
D.
liquid, vapor, liquid, liquid. So we have one option, option C and option D. Liquid, liquid, and vapor, liquid, liquid. So let's wait for some more answer.
And 4.
Sorry,
1, 2, and 4.
1, 2, and 4. Okay. So we have we have C and D, and we have A, C, and D. Okay. So we have 2 answers. You can use Aspen. You can go to the ternary diagrams option. You can check what kind of phases are allowed. You can see there.
C and D.
Okay. So the correct options are option C and D. Okay. So you can define liquid, liquid, vapor, liquid, liquid. Okay. So for the ternary diagrams in Aspen, we have liquid, liquid, and vapor, liquid, liquid phases. So, but in fact says you can also define with ternary diagrams, you can also find the solid actually, the solid carbon. Okay, carbon will be in the graphite form. So you can do the CHO ternary diagram. It will be useful who are working in the oil industry, maybe at higher temperature in the reforming. Okay. So you can use, I think some of you from the ONGC and all. So maybe they are working with methane reforming and all. So that the FactSet software is useful for them. They can use that also. They can use Aspen also. Okay. Residue curves or maps plot the composition trajectories of a binary mixture undergoing distillation at a total reflux. True, false?
True. True.
Okay, we have one answer true.
True.
And what is the reasoning?
Sir, I think false because it is for ternary systems.
Okay, so we have 2 answers. One is false, one is true. So first, the one who is saying false, please explain your reasoning.
Yes, sir. It's for ternary system.
It is for
Sorry.
ternary systems, so it is false.
Okay, yeah. So it's false. So it's not for binary, it's for ternary. Okay. DKMA database, just like NIST is freely available for Aspen Plus users. True, false?
False.
False.
Okay, so as we are having a question for database, so let's go to the Aspen and check the options
It's
available
subscription
there.
based.
Yeah. Just you can quickly go to the Aspen. So here you can see the database, okay, NIST, DKMA, DIPR. So if you go to the NIST, okay, so suppose I want to see the experimental data for my components, okay. So suppose I need some binary mixture, I have two components, so I need some data like methane, butane. I want to see the some experiment data, then click on the retrieve data. It will take some time. It will take some data from the server and it will show you. So here you can see some data, different datas, okay. So you can see the isobaric, isothermal, binary VLE 028, 081, number of data are there, okay. If you click like VLE 021, so at the bottom you can see the reference also. So this data is taken from this reference, and you can see the temperature, you can see the mole fraction, you can see the pressure. So if you want to use this data, then click on save data. So then you can, this data will be selected, okay. And you want to select more data, then you can select some more data also. And then this data set will be selected in your system, and you can use this data for the regression purpose, for the estimation, and like for the your analysis. So you can use this experimental data. Okay, just cancel it. So it is from the NIST. So this NIST is freely available. So because for the Aspen user, this data is free. If you go to the DKMA, so yeah, so here if you want to like methane and butane, then you can select the properties, what kind of data you want to search. Suppose I want to search the liquid vapor liquid equilibrium mixture, okay, then click it okay. So it will search. So here you can see some data are there, okay. So number of lines, you can see the price, you can see the system, you can see the year. So you can see some data here, okay. So if you want to purchase this data, just click on it, click on OK. You need to register on this website. You need to log in and you can purchase this data. You can see the price here. Okay, so this DKMI is not free. One of you is unmuted. Please mute yourself. So the DKMI database, just like NIST, is freely available for Aspen Plus. No, it's paid. So there are two calculation types that may be performed using data regression run mode: regression and space.
Evaluation.
Regression and evaluation. So we have one answer, evaluation. Let's wait for some more answer. Anybody? We have one answer, regression. So there are two calculation type that may be performed using data regression run mode. Okay.
Evaluation, sir.
Evaluation. So the correct answer is evaluation. Now let's go to the Aspen. Okay, so let's go first select a data. Suppose I want to select a data set. So let's select this random. Okay, save data. So if you see here, so we have a data set here. Okay, data. So it's saved. So in this way, we can save the data. You can see the options. You can see the data experiment data is here. Okay, the temperature, pressure, and all. Constraint, you can see vapor, liquid, and all. Then just go to the regression here. Regression is here. So your regression, you can see here we have DR1. Click on it. So you have two options: regression, calculation type regression, and evaluation. So you can do two. Okay. So there are two types of calculation: regression and evaluation. So the data regression mode is regression and evaluation. So if you want to, so data set, if you want to do something, then select the data set. Then you can check the consistency and all. First, let's check the consistency. First, evaluate. Let's say evaluate. Okay. Consistency, and click on run. Okay. First, I think we need to do the property run again because we have changed the data set. So we need to run it again, I think. After that, we will be able to do this. Okay, so we can try it later. So the data obtained from the Einstein D-gamma can be used by the regression tool for the analysis of the model. True, false?
It's true.
So we can use the data obtained can be used for regression tool for analysis of the model. So we can use it. It's true. So these are the questions for today. Now we can go back to our slides and we can do some examples. So yes. So we have some problems on pure component. So let's see about the user defined. Okay. So property estimation of user defined. So let's see how we can define our properties in Aspen. Go to the components. Then here we have option user defined. Okay. So if you click on it, then you can see you can have some components here. Okay. So like for methane, we have already component ID and all. If I go here and I click on user defined, then this component I can enter. Okay. So we have given the question like vanillin. So just type it. Okay. You can define the type. So the required properties for conventional component include. So if you want to define a conventional component, then you need to define molecular weight, normal boiling point, structure, vapor pressure, and ideal gas heat capacity. If you want to define the solid, then you need to define molecular weight and vapor pressure. If you want to define non-conventional, then you need to define models for calculation of enthalpy and density. So these are things you know define. So suppose it's conventional, you click next. So here you can see the molecular structure. So you can draw, import or edit structure. Suppose if you have a component already, just you want to edit that component. So you can edit that structure here, and you can just edit all the parameters, and you can also import. Okay. So just click on it. So here you can see. So you can draw. Sorry.
So the component ID, please.
Component ID, actually we are defining a new component. So suppose here, like you have methane. So methane is available in the database. Okay, butane is available in database. Let's say I want to select water. So if I click H2O, so it's H20 actually. So if I click H2O, then automatically detect water. But suppose a random component is like component name CX. Okay, so there is a component X. I want to define this component. Then I click enter, then you can see there is no CS number. It means that this component is not available in the database. So, but I want to use this component for my model. Okay, you are developing a system, you are performing some analysis. In that analysis, you have that component, but Aspen database don't have that component. Okay, but you know the structure, you know the data for that component, so you can define yourself that component in the database, and you can use that component with other already defined methane, butane, steam that is defined already in the Aspen. You can use that component. Now suppose if you don't define it and directly use this component, then your system will not run. You will have some errors that will show you that your component CX is not defined. Aspen is not able to calculate the properties for CX. So you will have some errors. So you need to define it. So to define it, click on it, user defined. So you can see your ID is CX. So you can give your ID or like CX. Okay. So your component, you know the component is conventional, solid or non-conventional. So based on the type of component, you need to define the properties. So let's say the component is non-conventional, then you need to define these parameters. Okay, you click on next. So here you can draw your own file, like you know the structure. Suppose you know the benzene, there is a benzene, then you know there will be some structure, then some bonding will be there. So basically you can define, okay, you can define your structure, or you can also import. So there is a website, chemical book. So the chemical book is website is there. So here you can find some, you can enter a component, okay, and you can like, so if I enter methane, so it's not coming really good. Yeah. So I think this site is not working good in my system. So due to some issue. So here you can see for methane, the CS4 is there. Okay. The molecular formula, molecular weight. Okay. So here you can have a mol file, MOL file. So you just click on it. So this file is downloaded. Okay. For any other component also, you can search the component, you can download this file. So this file have structure of the component. You can import that structure directly into the Aspen. Okay, so I think there will be an import option, import mol file. So if you go to the downloads, okay, actually, yeah, I am in my different computer. So if you go to your download folder, okay, then you will find that particular file. You can directly import that. Then you can find on the like Wikipedia, on Google, or some database from some journal, okay, from some reports or like any source that you have. So you have to enter the molecular weights, just random numbers I'm entering. Okay, so you need to enter this data, then just click next. So you need to define like if data is not in the range that a particular range should have, then it will give you some error like this. Okay, so the specific gravity 0 and 3, between 0 and 3. So then click on next. So then it will evaluate now. So you can also evaluate if you have some database with this. If you can also estimate using the property estimation system. So these options you can use. So you can define in this way your own component based on your data. Okay. So this is about the then verify whether enthalpy of toluene is affected with change in pressure from 1 bar to 20 bar in the range of -50 to 150. Use predictive SRK property method. Just try it. Let me know the answer. Just have 2-3 minutes. Just try it. So you need to go to the analysis, pure component. You have given the components. Okay. So here you have given this toluene. Okay. You have given a pressure range 1 bar to 20 bar, temperature range, and predictive SRK. Just quickly try it. Let me know. Anybody is trying? Is anybody trying? Let me know, please.
Yes, we are. I'm trying.
Okay, okay. So just define the component, okay? You need to see the thermodynamic property enthalpy. Use the analysis tab.
The liquid phase is almost same. Vapor phase is
Okay.
varying.
Okay, so let's see. So if you go to the Aspen, then just define the component. Okay, following, then next, then the property we have given the predictive SRK. So yeah, PSRK. Okay, so define the property, then next, then run it. So now if you go to the pure, the analysis tab, pure, okay, then here you can see the multiple options. So property type. So you can see which you can analyze thermodynamic property, transport property, all or EOS alpha function test. So we have given in the question, you have to see the analysis of enthalpy. So enthalpy comes under thermodynamic property. So then property, which property is there? Enthalpy. So what is the name of enthalpy in this?
H.
H. So H is enthalpy, okay? So you need to see the name. You can also take the help of Aspen knowledge. If you don't know, you can click on this individually. You can see the name. Like this G is the free energy of pure component. FUG is fugacity of a pure component. So H is the enthalpy. Okay. Then you have given the enthalpy of effective change in pressure. So you have given the pressure range, temperature range. So the phases, then check the vapor also. Units, you can define the unit of enthalpy. Okay, then the temperature, then you can give the start point and the end point. So what should be the start point? Let me know.
Minus 50 degree.
Minus 50. End point is
150.
150. Okay. Then I need to select the component. Okay. Anything else?
Pressure 1 bar.
Yeah, pressure is 1 bar. Okay. So the method PSRK, okay, everything is fine. Then click on the analysis. So here you can see the graph. Okay. So if we change the pressure 1 bar to 20 bar, then what will happen? So this is for 1 bar. So you can type here also, you can change the rename the legends bracket. It's for 1 bar. Also for 1 bar. Okay. So you can see now 1 bar is mentioned here. Now go back to again, then just change it to 20 bar. Then run analysis. So you will have another curve and it's for 20 bar. Just change the legend so it will be easy to understand the comparison. Okay, now I think we have a merge option.
For that, we have to open another tab to do binary analysis at different pressure.
Okay, yeah. So actually, yeah. If you use the same, okay, then it will overlap that. Okay, so that previous one is gone. So you need to do it again. Okay, just do it again. Yes, so this is for 1 bar. So now we have this 1 bar, and this plot is for okay. Why this plot just went away? Okay, why they are not existing both actually? What is the issue? Do we need to do it again? Why I'm facing this problem? So this one is for 1 bar. Okay, if I go back to again, so we have pure 1 and we have pure 2. Okay, so just let's this change it to 20. Yeah. We have pure 2 is 20. Okay. Okay, anybody wants to tell me why they are not existing both? Because I am running two analysis, pure 1, pure 2, but still I'm only having 1. Why? Okay, I need to check it. Why I'm not getting all the two graphs together? Because here you can see we have two analysis, pure 1 and pure 2. In the one, we are using the pressure 1 bar. In the other, we are using the pressure 20 bar. So there should be two plots, and then we can merge those plots. But I'm getting two plots tab, but the plots are only in the one tab. Okay. Okay, so I will check it later. So you can do it. Maybe I don't know where I'm doing wrong. Okay, now I can see the data in both too. Okay. So
You have to go to the pure component option again, sir. Then you can get the two plots.
no, I'm getting the two plots together, but like this I'm not getting. Suppose I'm running it for 1 bar again. So I have one plot here, okay? So let me just rename it like this.
Okay.
Okay, then I'm again going to another analysis in pure 2, in which 20 bar is there, and I am doing it again. So I'm having another plot, okay? So My previous plot is not visible then. So if directly I just click on the merge, I think then they are appearing both, but not as I want actually. Why it's happening, I don't know. Okay, so let's see. So I think, okay, so you can check it option. So maybe I'm missing something. So you can do it at yourself. So in this way, you can have all the graphs. So click right click, then the y-axis. So you can have a single y-axis. So you can compare. Okay. So there is some change. So for the, you can see for the liquid, we are having change. So the green and the magenta, you can see for the liquid, we are having change, not for the vapor phase. Okay. So in this way, you can compare. Okay, so I think it's enough for today. So now, like, let me know how are you using Aspen? Like, everything is having any issue in installation and all, everything is fine or not? Because I think in earlier classes you were having some issues regarding installation and all. Okay, so I think it's fine for everyone. So anybody have any question regarding anything? We have 5 minutes, so we can discuss a general question if you have. Okay, so anybody has started using Aspen for their work? I think earlier some of you were from some industries. Some of you are from some industries. So have you like have you started working with the Aspen regarding your project or your work? Okay. Okay then. So anybody wants to share anything regarding Aspen? Your experience till now for the 5 weeks? Want to share your experience so we can like improve further? You want to share your experience? You can share it.
Sir, I have a doubt, sir.
Yeah, Priyanka, please.
So the thing is, I installed it today, Aspen 14th version. So all these
Okay.
days I was facing some issue. So yeah, I finally got that installed. So today, initially you said this topic, no, sir. I mean the question about methane and butane, like 2:1 ratio. So I did that, but the thing is, under analysis, in the properties under properties tab, I mean under analysis you got pure I mean you got certain subtopics, no sir, that is not appearing on my version. So could you say the reason behind that? What might be the reason behind that? I mean, like, am I not doing it
Okay.
properly, or
So no, first you need to run the property, I think, because that tab will be, I think, with the change of version, the tab will not disappear suddenly. So just you need to define the
yes,
components first, okay? Then you need to define the property method. You need to run the property first. Then only you
yes
will
sir,
be able to see the analysis.
get the
Have you run?
yes I get components, that is methane and butane, and
Okay.
after that the method, I mean the Peng
Yeah.
Robinson, I entered
Have you
that.
defined that?
Then,
Okay.
yes, sir, I did define that. Then after that, I mean, you have to give the mole ratio, no, sir, the 1:2 under
Yeah.
analysis.
Yeah, so if you go to the home tab, then there will be option analysis. So maybe if your version is changed, so you can check other options also. You will find some analysis tab. In that tab, all the option should be there, like pure, binary, ternary, and all. So find that option. Or you can
No,
also,
under
Yeah.
analysis, when I clicked on analysis, what appeared was name, type, hide, active, status, description, delete. These are the things that opened. Like I could not see
No,
any.
no. You clicked on analysis, I think.
Yes, sir.
Don't click on analysis. Analysis, I think the analysis above the estimation, regression. Don't click on that analysis. That analysis is different. Just go to the analysis tab actually. So let me show you. So I think when you clicked on this analysis here, note this. So
Yes,
if
sir.
you see here, you can see the analysis option. So here you will see this pure binary mixture and all. So this is a control like summary, analysis, run more, data source, tools. So here you will see these options. Okay. This is a different analysis. You can do like property estimation and all. You can do it here. So also if you click on this also, then you can also find these options. But directly it will be find easy here actually. So if you click on this option, then you will find these options. Okay. You will have a data set. Click on this data set. Then you will find some analysis here. Okay.
So could you once again say on which analysis I am supposed to click, sir?
So you can have directly here like pure binary mixture. You can see here. You can see my arrow.
Yes, sir.
So I think you can see in your Aspen also, you will see some options here, direct options. So you can click on these options. Like if you click on PT envelope, so directly you will come into this.
Yes, sir. Thank you,
Okay,
sir.
or you can also go into this analysis also. You can, if you click on this analysis also, then you can also go. So you can see here, you can see then 3 options are there. But first you need to select it from here. Then only they will appear here. Suppose if I delete it, then if I've deleted all the analysis, then if you click on it, then it will be like this. Then you need to select from here. Then click it new. Then you need to select its type. Generic. Oh, so generic is here actually. So we will discuss about the where is the generic. So if we click on this analysis, then we don't see the generic. But if we click on this analysis, and from here, if we select the option, then we can select here the generic. So generic, PT envelope, residue, and ternary diagram. So in the generic option, I think we have further options. So you can explore these options. Okay. So you can
Yes, sir.
explore these options, or you can also directly go to here also. It's pure PT envelope also. You can also go to here. Okay.
Yes,
So
sir.
as we were
Thank
discussing, so as we were having discussion earlier, where is the generic? So for all of you, the generic is here. If you click on the analysis, and if we click on new, then we can see the generic type is here. So it's under analysis. So that's why the generic is here. Okay. The generic, the PT envelope, they comes under the analysis. So here is the generic. If you go to the generic, then there are some other options. Valid phases, then the variables. So you can explore this option. Okay. Okay. Thank you, everyone. Thank you for joining, and I hope you will join the next week also. Thank you.
Thank you, Amit.
Thank you. Bye bye.
Thank you, sir. Bye-bye.